Hey all, it's Andrew Couch here, and in this Tidy Tuesday video, we're gonna be going over autoencoders. I know I haven't really been going over the actual Tidy Tuesday weekly data sets, but I figured it'd be kind of more interesting to go over neural networks. So I thought it'd be fun to make a video on autoencoders. Um, so what are autoencoders? Well, autoencoders really just comprise off of two models: an encoder, which essentially condenses the data into a specific amount of features given the nodes, and then a decoder, which will basically retransform that condensed data into the original input. And one way to think about autoencoders is about like image compression, where we're essentially compressing like a 10 megabyte image into a 2 megabyte image. So the actual underlying structure has changed, but from a visual standpoint, it looks the same. So you can see for this original input to a restructured input. And that's the actual autoencoder going to work and basically recondensing it to this specific format and then reprojecting it to what it's supposed to look like in its original format. We can also look at it from, I guess, the neural network architecture point of view. So we can see how we have our inputs. We can decrease the inputs, so it's condensing it, and then we can see how this is essentially like the bottleneck or the minimum amount of how much we're essentially condensing the data, and we're reprojecting it. I'm also going to be going over for autoencoders is the credit card fraud data set. I think when I think about autoencoders, you think about anomaly detection or just embeddings. So we're going to do these two examples. We're going to do a anomaly detection problem and also an embeddings problem. Okay. I'm going to open up a R markdown file, and I'll call this Tidy Tuesday Auto Encoder. So one thing that I will say is I don't have the data set in my repo. You're going to have to go on kaggle.com and download it yourself, because I didn't want to basically mess with the storage in my own personal repo. So we're gonna load in 3 packages: the tidyverse, Keras, and tidy models. We're gonna read in our credit card data. So it's credit. I have it named credit card.csv. I'll say load in from kaggle.com. Okay. So if we look at our actual data, we can see we actually have a decent amount of features. One thing that I'm gonna remove is time. I think that's supposed to be something to do. It doesn't have a lot to do with the actual transaction, so we're going to filter that out. And these V features, I think, come from like some type of principal components analysis. We also have the amount and also the class that we're trying to predict. And our class is like 0 and 1. And we can see our average positive class is less than 1%. It's like 0.1%. So let's do some cleaning. So I'll say mutate class is equal to if else class is equal to 1, then we'll say it's fraud, else it's no fraud. We'll turn that to a factor. And then we'll also select minus time, right? We can also see we have 284,000 rows, which is a lot of rows, but it's good for neural networks. And then we can see that we actually did the thing correctly. So that's just some basic cleaning right there. We're gonna have to do some more cleaning, but I want to first go over how we can use autoencoders in our own problem to detect anomaly detection. And one of the main ideas with an autoencoder is we're trying to basically teach it what we should be expecting to see and having it reproject it. So in this case, what we're trying to do is we have a highly imbalanced data set of non-fraudulent transactions and fraudulent transactions. We have a lot of non-fraudulent actions. So we can basically teach the model what a non-fraudulent action looks like and then have it project all the actions. So when it sees a non-fraudulent action, ideally, since it's seen so many other non-fraudulent actions, it will be able to remap the data into the actual original data set. However, since fraudulent actions should be a little bit different, it shouldn't be able to remap the fraudulent actions in a correct space. So if it can't reproject the data to its original data set, then we can kind of confidently assume that this transaction is a fraudulent transaction. So how do we actually do that? First, let's actually do some data cleaning. So let's create our train and test splits first. I'll do set.seed is 42. I'll do a tidy split is equal to initial split df, and we'll stratify based off of class. We'll create our train data, which will be a training tidy split, and our test data, which will be our testing tidy split. What we also want to do is split our train data into a fraudulent and non-fraudulent data set. So train data filter class is equal to fraud. We also want to deselect our class. And then we'll also do a non-fraud df, and we'll do the same thing, but say it's not fraud. So let's say exclamation point, no fraud. Okay. Ooh, actually, we could just, I'm going to copy this right there. We also want to do some pre-processing to our data set. So if we look at our trained data, I'll do that. Our trained data, if we look at the summary of it, we can see that our min and max is all over the place. And neural networks like values between 0 and 1. So we could do some min-max normalization, or we can do the tidy way and use the range, step range pre-processing. So we'll just do that. So we'll do tidy rec recipe. We're trying to predict class. A equals train data. We'll say step range all predictors. Boom. Right that. Tidy rec prep bake, and we'll apply the recipe to our train data. Sorry about that. I just screwed that up. We'll apply that to our train data. Where's our train data? Our train data. And we'll also apply it to our test data. So test data. Right? And if we look at our actual train data, we can see our values are between 0 and 1. Same with our test data. Good. Cool. So now what we're going to do is split our train data into fraudulent and non-fraudulent transactions. And what we're going to try to do is create a neural network to look at our non-fraudulent actions. One thing that I will say is, once we have these data frames or tables, we want to convert them into matrices. So we're just going to say as.matrix. As.matrix. Cool. And now what we're going to do is actually define our autoencoder. So autoencoder, and we'll say Keras model sequential. And with our autoencoder, we're going to have to select or define our layers. So our first layer will be a dense layer. Our units will be 15. Our activation will be a ReLU activation. And our input dimensions or input shape will be the amount of features we have in our matrix. So we can say non-fraud df. If we do our end call, I believe it's end call non-fraud df, we have 29 columns. And it's going to take those 29 columns or 29 nodes and output them into 15 nodes. We're also going to do another layer, which will be a 5-node layer. Okay, and then we'll also do another layer to go back up. Activation equals ReLU, and our last output layer will need to be the amount of features we have in our non-fraudulent DF, because we want to basically remap our features into the same amount of features. Cool. So we have that. We also will do a compile. So with our compile, oops, usually we put it right there. When we compile our model, our loss function will be mean squared error, and our optimizer will be atom. And we choose mean squared error because it's essentially going to project the data, our our one transaction to the same transaction. And we want those values to be basically the same, even though we condensed it. So we basically penalize it between how off it is from the original value. Cool. So we have that. And now what we can do is actually fit the autoencoder. So I'll say autoencoder history, and I'll say autoencoder fit, and we'll give it our X and Y's. And what's interesting about autoencoders is we're actually going to give it the same data sets. So non-fraud DF, epochs or epochs is 100, batch size will be 32, and then we'll do a validation split is equal to 80-20. We're also going to add some options, which we'll do our callback. So we'll just enable early stopping. And for our early stopping, we'll just say that if we don't see any improvement in our validation error, then we'll just stop the neural network early. And we're going to have to wait like 10 epochs for it to do it. So we're running the neural network. It's going to take a little bit. Hopefully it'll stop a little bit earlier. So let's let it run. And we can kind of evaluate what it's actually doing. You can see the loss, validation loss, and it should just improve as it goes, but then it'll probably stop in like 20 or 30 epochs. And also, if you want to check, it should have the we should have a little interactive chart right here if we wanted to actually look at that. So once we actually train our autoencoder, we're gonna actually predict it based off of our other our non-fraudulent and fraudulent data set. And we'll see how it's able to basically remap the non-fraudulent features better than the fraudulent features. And that'll be good for an actual model. Okay, so I'm actually gonna rewrite these models. So I'll just say like, oh, we're gonna use our autoencoder. We're gonna give it our non-fraud DF, and we'll also say predict our autoencoder and give it our fraud DF. And we'll give those our predictions. So we'll say non-fraud pred, and then we'll say our fraud pred. See, you can see how it's saying it might stop the training, hopefully. So it's ruptured promise evaluation. Okay, so the model finished training. I accidentally messed up the option for callbacks, so it went through the entire iterations, but that's fine. So we trained our model to look at our non-fraudulent data sets. I'm going to predict based off our fraudulent and non-fraudulent data sets. Cool. So our non-fraud predictions are actually in a matrix. So if I do a head, we can see it's in matrix format. Luckily, R, again, is a statistical programming language. So to do matrix math is pretty easy. What I want to basically calculate is essentially the sum or the total squared error between each feature or each transaction. So let's do that. So this is our non-fraud prediction minus our non-fraud actual, right? And we'll square that, and then we'll just calculate the row sums of it. So row sums of the squared error. So we have that right there. We can call this a tibble, and we'll say total squared error. Cool. All right, so we have a total squared error for all of our observations, 213,000 observations. We'll do the same thing with our fraud predictions. So if we do that, oops, right there, total squared error. Now let's actually look at the summary of it, of the errors for each data set. What we can see here is our mean and median is 0.01, 0.02. And for the actual fraudulent, we can see it's a little much higher relative to the actual scale of it. So we can see how we can actually detect some type of error in our model. So now that we have this, one way to actually calculate or create an anomaly detection model is to use those errors as features. So let's actually do that. So I'm going to actually go back to our trained data right here. Our trained data. I'm going to select minus class, select minus class. And I'll do the same thing where I'll basically say, I'll use our autoencoder to predict based off our trained data. Right? Oops. And we have to convert that to a matrix. And then we'll subtract that to our trained data, select minus class as dot matrix. Right? So this is our residual. We'll square it, and then we'll calculate the row sums of the squared residual. And then we'll convert this to a table to error. And that's our final. So that's our actual error right there. And then what we can do is bind our columns of our trained data, and we'll select the class. And this will be our model data. So with our model data, if we actually do a group by class, and we'll do like a short summarize equals to mean error, we can see the fraudulent transactions have a higher error because our autoencoder does not understand how to basically reformat these fraudulent transactions, and will instead remap it to a non-fraudulent transaction. And these, the difference between a non-fraudulent and fraudulent action will cause a larger amount of error. And that's the big idea between these models. So let's actually just create a logistic model. So I'll say anomaly, I'll say anom model because I don't know how to spell anomaly model. I'll just say logistic reg, penalty is equal to 0, mixture is equal to 0, and we'll fit it to class to error data is equal to model data. Great. So we have our anomaly model right here. We can actually show, let's see what our actual model can fit in its in-sample predictions. We'll just say bind column to model data, select class, and we'll say conf mat truth is equal to class, estimate is equal to dot pred class. Right. So it's not doing great. But out of all the fraudulent transactions, it can detect 27 out of them. Obviously, if we do a logistic regression, I'm sure we can actually do a little bit better. So let's just do that. So baseline model, and we'll just say logistic reg to our train data, and let's do train data to that. Okay, so train data, we'll give it our baseline model, our train data, and let's see what it looks like. So our logistic regression model did a little bit better, or did actually a lot better than our anomaly detection model. But that's fine because generally, nowadays, people don't really use autoencoders for anomaly detection, but they used to be used for it, and I thought it'd be a kind of interesting video to do a actual video on it. We'll do our final test set predictions. So let's do that. Predict our autoencoder, and then our test data, select minus class and the as dot matrix. And then we'll just say, we'll calculate the squared error. So let's say, write that. Oops. So we'll just do that. And then we'll say, we'll calculate the total squared error right here. So row sums of that. And then hopefully that'll do that. Yep. And we'll say and we'll say table error is equal to that. and bind our actual labels to our data set. Oops, test data. Okay, so that would be our eval set. Okay, and then we'll say predict our eval, our what is it, our anomaly model on our eval set. And then we'll bind our columns to our eval set, and we'll do our confusion matrix. And I'll select the class. Okay, so we see our model did not do very well. Let's do, let's just evaluate on our test set just to see how our baseline model were to do on this problem. And we see it did a lot better. And that's why autoencoders are not that great for anomaly detection, but what they are very good at is dealing with creating your own embeddings or your own little clusters to be used for other analysis. So we're actually going to do a part 2 on this and deal with image data. So let's actually do that. Let's load in the MNIST dataset. So let's say MNIST, was it data, Keras, MNIST, dataset MNIST. Okay, so we have that. What else can we do? So then we can do our X, or let's say train X, which will be our MNIST df, was it train X? Then we'll say train Y, which will be our labels. I'll say a train, no, I'll say train Y. So that'll be our labels for our data set, train Y, and we'll do a test X, which will be our testing labels, and then our test Y, which will be the test labels. So the X will be the actual pixels, and the Y will be the actual labels. So we have it both split in our train and test sets. Okay, we'll do that. One thing that we'll also have to do is normalize it. So our test X will be our sorry about that. Our test X will be formatted. So if we look at our test or train X, we're gonna have to do some pre-processing. We're actually will do maybe a summary. So 255. So if we do train X divided by 255, and then we do a summary, we essentially did a min-max normalization. Cool. So let's do that. So train X is equal to that. Test X is equal to test X. Test X is divided by 255. If we also look at our data set, our images, we can see that it's in 60,000 images, 28 by 28 pixels. We actually want to reshape these pixels. So because we're not doing any convolutional neural networks, we're just doing a densely layered neural network, we need to flatten this. So we're just going to reshape these images or these matrices. So we'll give it our train X, our dimension, we'll just say n row. So train X, and we'll just say 28 by 28. So essentially we're going to be converting this square into a long line. And we'll do the same thing for a test. So we're saying like this is how many rows. Boom. If we look at our variables, we can see that we basically converted these squares into a long little line that's 28 by 28. So it's just rechanging it. Cool. So now it's actually making an image autoencoder. And it's literally the same thing for any other autoencoder. So we're going to define our sequential model. And then we'll start doing our layers. We'll start initiating our layers. So layer dense. In this case, since we have 228 by 28, so 784, we're not going to use 15. I'm actually going to use like 256. So units equals 256. Activation is ReLU. And then what else? Oh yeah, input shape is equal to n call train x. Actually, let's see here. 28 by 28. We could do 512 actually. I'll do 512. Cool. And then I'll do another layer. In this case, I'll just do 256. Activation is equal to ReLU. A final layer, which will be, in this case, let's just do 8 because I have an idea of how to show these layer embeddings. So we'll just say 8. So we're essentially going to use these 8. We're essentially condensing these 784 features into 8 features. Activation is equal to a ReLU activation again, and then we'll just copy and paste this other stuff. Obviously, we have to remove this input shape. And then our layer dense output will be the number of columns in our actual data, or the number of features in our actual data. Great. So now we have that. We can do our image encoder, compile. Our loss again will still be mean squared error, and our optimizer will be atom. Okay. We can also show this summary of the neural network. So summary of autoencoder. We have this many layers. We can see how we have our little dense layer right there. One thing that I'm actually going to do is actually rename it. So I'll say name is equal to embedding. Because in this case, we're actually not going to do any anomaly detection. We're going to use a neural network to basically use it to create a layer embeddings, or to basically condense our features into our defined amount of features. In this case, 8. So once I have the name for it, it'll just always call it embedding. Okay. Sorry about that. I accidentally exited the the OBS recorder. But we're going to actually train up our image autoencoder. So image history. We'll do our image encoder. We'll fit it. Our X will be our train X. Our Y will be our input. Our epochs will be 50. Our batch size will be 128. Validation split will be 80-20. And I'm not going to mess up the callbacks, so I'll say callbacks is equal to callback early stopping patience is equal to, we'll do 5. Epochs and epochs batch size. Train X, what did I do? Oh, there you go. Go there. Oh wow, I forgot my commas. Okay, so now we're going to train up our neural network. So we're essentially doing the same thing as our autoencoder, but instead of actually using the error rates in our outputs, what we're going to do is actually take the outputs from one of our layers. We're going to let this run, and I'll probably get back to you after this model finishes fitting itself. Okay, the model finished fitting, and now we can actually look at it. So with our image encoder, we have a autoencoder like our previous state, but what we actually want to do is extract the outputs from this layer only, which will essentially output from our given 28, was it 28 times 28? Our 784 feature data set, we can basically condense it to 8 features. And the way to do it is we're actually going to create a separate model called the image embedded, we'll say embeddings model. And what we have to say is Keras model and our Keras model has our inputs and outputs. In this case, our inputs will be the same inputs used from our original encoder. Let's say input, but our outputs, our outputs will be our image encoders. We'll have to retrieve the layer from our image encoder model. And what we already know is we named it embedding. So embedding. And then with this layer, since it's essentially extracting the layer from the model, right? We can just say we want the, output. Cool. And now if we actually look at our embeddings model, we can see it's the same image encoder model, but it's essentially chopped, where you have the output as our embedding layer. So what does this mean? Well, we can actually predict using our embeddings model. So we'll do that, and we'll just predict it based off our x, our train x, right? Because this is the data that we originally trained it with. Okay, and you can see we have 8 embeddings. We can convert this to a table. So as table. And then we can also add the labels. So say bind columns, train y. And we'll say table labels is equal to train y. Okay, and we can see how we have our 0 through 9 digits. And we'll call this our model data. Actually, I want to mutate something. So I'll say mutate labels is equal to as factor labels. And this will be our image model data. So essentially we condensed 784 features into 8 embedding features with our label data. And one thing that's kind of cool is we can actually train a multinomial logistic regression to do some image, computer image or computer vision modeling. So let's do that. So let's create a multinomial, we'll say a image model, and we'll say multinomial reg. Our mode will be mode is equal to mode is equal to classification. Penalty is 0, mixture is 0, and we'll fit it. Given our labels, data is equal to image model data. Okay, and now let's actually do our eval image. So we'll say predict our embeddings model, our image, our embeddings model with our train, our test data set, which will be our test X. And then we'll predict our image model given our eval embeddings. Oops, and then we have to say eval image, and we'll say as a tibble, and then let's bind our columns to our labels is equal to test y. So we have our labels, and then we do our confusion matrix. So truth is equal to labels, estimate is equal to dot pred class, and I have to do a labels is equal to as dot factor labels. What's here? Right. Estimate. And then we can do our confusion matrix. Truth is equal to labels. Estimate is equal to dot pred class. And we can see how our basic logistic regression did very well with a multi-class classification problem, where we essentially reduced 784 features into 8 very high information features, and we got some nice predictive power from it. which is one of the good things about autoencoders is we essentially generate and do some feature reduction using neural networks. So I know this is a pretty information-packed video, but I hope it informed you guys, and I'll see you guys next week, and tidy on.